Hi folks, welcome back to Physics with Captain Rod. So the purpose of this video is to demonstrate how to use the idea of equivalent capacitance to simplify a capacitive type circuit down and then find all the voltages and charges on each capacitor. So what we're looking at here is we have a circuit with a 10 volt potential applied. A capacitor combination here. We got a 3 microfarad, a 4 microfarad, a 2 microfarad, a 1, and a 5. And because of the 10 volt potential, this battery is going to push charge in the circuit in a clockwise sense. So these capacitor charges, I've already put them on here. We're going to have like a plus here, minus here, plus minus, plus minus, plus minus, plus minus. So these capacitors now are going to be charged, and I'm going to give those charges names. I'm going to go through and just kind of name them here. I'm going to call the charge in this capacitor Q1, and this one Q2, and I'll just list them over here. The charge on this one Q3, on this one Q4, on this one Q5. Alright, so we have basically 5 unknowns, but the first thing we can say right away is this. The current anywhere in this branch has to be the same. Therefore, if these capacitors started all initially uncharged, whatever charge went on to Q1, the same charge has to go on to Q2. So Q1 and Q2, they have to be equal. I'm going to go right now and just erase this 2 and just call it Q1 now. Whoops, except get that in my pen color there. Okay. Now, as we look at the circuit here, the first thing to recognize is we have these 3 in parallel. These can be simplified. A 5, a 1, and a 2, these are going to add to 8 microfarads. So what we do is we redraw the circuit, keeping everything else identical. So we got the 3 microfarad, the 4 microfarad, and in the place of this combination, we're going to put a single capacitor now, 8 microfarads. Now, charges. So the charge Q1 is the charge on this capacitor. Right? Charge Q1 is also the same on this capacitor. And now we're going to have a charge on this capacitor right here. And that's the charge. It's not Q3, Q4, or Q5. What it is it's the sum of them. I'm going to put how about 3, 4, 5 on it. 3, 4, 5. This is not a charge that we directly need, but it's one that will, I think, help us out here in the next picture. Also, before I move on to do the next picture, I'm going to take a moment now and kind of color code the potentials. I think that's a great way to visualize these circuits. So I'm going to start with red. The highest potential in the problem is right, oops, that's not red, is right here. This is all constant potential because it's conducting material up to that point. Across the capacitor, however, we are going to get a voltage change. So we're going to get a voltage drop. We're going to be at a new voltage here. I'm going to call that the orange voltage. All right, we're going to get a drop across here. I'm going to color code that in green. And that potential is constant all the way, anywhere it's conducting material. And then on the other side here, we're going to have what I'm just going to call the black potential. And that's going to be the lowest potential in the problem. All right? Now, picture on the right. Let's see. The black potential, I'll just work it backwards. The black potential is here. And then this one was green. And then this one would be the orange potential. Then again, we're back to red. All right. So now we got our voltage changes in both pictures. I think pretty well established. All right. Next, we take a look here. We have 3 capacitors now: the 3, the 4, the 8. These are all in series. So to find the equivalent capacitance, we would write, oops, 1 over C equivalent is equal to 1 over 3. I'm going to leave the units out. They're all consistent. They're all microfarads. 1 over 3 plus 1 over 4 plus 1 over 8. Put a little NCU for note consistent units. And when we calculate C equivalent, right, and what you do is just take in your calculator and go, 1 divided by 3 plus 1 divided by 4 plus 1 divided by 8. Hit equals, but don't forget you have to invert your answer. And what I find is that the equivalent capacitance of the system is 1.41 microfarads. So we can replace those 3 capacitors with a single capacitor whose value is 1.41 microfarads. And here's our 10-volt battery here. And I'm going to go ahead and color this potential. Remember, that's our red. Whoops, I could have done a little better job than that. This is our red potential in our problem up to this point. And the other side, black. Okay. So now we've got this circuit simplified down. We have some sort of charge on this capacitor. Right? This is charged plus minus. The charge on that capacitor now can be calculated because the voltage across it, and again notice, red to black, and I come over here. Red to black is 10 volts. So the charge on that capacitor is going to be 1.41 microfarads times 10 volts. Remember, a volt is, or a farad is a joule per coulomb. So when we take a farad is a coulomb per volt. So when we take coulomb per volt times volts, we get coulombs out. So our charge is going to come out to be 14.1 microcoulombs. That's the charge on our equivalent system here. All right, now the important thing is how we go back the other way. We got to kind of work over to this picture and then over to this picture. So, the 14.1 microcoulombs. It's important to understand how that relates over to here. And again, this is a single system here. It's a single branch. I like to do the branches in green. Notice there is just one basically wire that goes around the system. And what that means is whatever charge passes through this point, the same charge has to move through here, and through here. So what that means physically, all of these charges are equal, and they are all 14.1 microcoulombs. All of them. I'll just do this. Oops. All of these are 14.1 microcoulombs. Now, 2 of those are ones we wanted directly. This Q1 is the charge here, so that charge is done. This one is the charge here, we're done. This one, however, isn't the ones we want. What we want are Q3, Q4, Q5, and what we have is Q3, 4, 5. And what I meant by that is that's the total charge on the system. So the 14.1 microcoulombs is good here and here, but not over here, not for these. What is true is the 14.1 is the sum of these 3. Now, as far as how do we calculate these guys? Well, what we need is the voltage across each of these. Notice that the voltage is the same. Green to black, green to black, green to black. And I look over here in this picture. Green to black is the voltage across that capacitor. So we can calculate that. Remember, let's see, capacitance is charge over voltage. Right, so rearranging that, voltage is equal to charge over capacitance. So the voltage across the 8 microfarad capacitor is going to equal 14.1 microcoulombs over the capacitance of 8 microfarads. And when we work this out, I get 1.76 volts as the voltage from green to black. Right, so now what I'm going to do is take this voltage again, taking note, that's from green to black. That means in this picture, the voltage across here, here, and here is 1.76 volts. So now, charge 3, we can say, is equal to 2 microfarads times 1.76 volts. And I get 3.52 microcoulombs out of that. Right. Charge 4 is equal to 1 microfarad times the voltage 1.76 volts, and that one is 1.76 microcoulombs. Charge 5 is going to be 5 microcoulombs, microfarads times the voltage 1.76 volts. And for that one, let's see what do I get when I calculate that. I get 8.8 microcoulombs. All right. One of the questions I get all the time: how do we know when we're right? And I always mention this. In life, there's no big book of answers. You have to know how to check the problems for things that you know. So right now, I'm going to stop and do a quick check. This charge right here, Q345, that's the sum of these three. So I'm just going to stop and check and make sure that the sum of these is equal to the previous one. So 3.52 plus 1.76 plus 8.8. Whoops, and for some reason my calculator gave me an error. Try that again. 3.52 plus 1.76 plus 8.8. I get 14.08 microcoulombs for the sum. And I look back over to here, Q345 was 14.1 microcoulombs, and that to 3 sig figs, that rounds to 14.1, so at that point we're happy. All right, so we move on. We now know the charge and potential on all three of these. Getting back to these guys, we already know the charge on them from right here, 14.1 microcoulombs on both of them. I'll go ahead and write that down, 14.1 microcoulombs and 14.1 microcoulombs. The only thing to calculate now are the voltages. So remember, voltage is charge over capacitance. So the voltage, the red to orange here, is going to be the charge, 14.1 microcoulombs. I'm sorry. The voltage is charge over capacitance, and the charge is 14.1 microcoulombs. Divide by the capacitance, 3 microfarads. And I get 4.7 volts. And again, that's the charge, or I'm sorry, that's the voltage red to orange. So I'll go ahead and label that here. That's 4.7 volts. And I'm going to go ahead and calculate this one. The voltage from orange to green is going to be the charge across that capacitor, 14.1 microcoulombs, over the capacitance, 4 microfarads. Let's see what we get out of that. 14. Double check that against this. Okay, I got 3.53 out of that. So there's the voltage across here, 3.53 volts. The only thing left to do is to now check one more thing. As a check, as I look here, from red to black is 10 volts, and red to black should be the voltage when I look over here across red to orange, plus orange to green, plus green to black. So our check here is 4.7 volts plus 3.53 volts plus the green to black voltage, which I know I have listed somewhere, 1.76 volts. And see what I get as a check. Keeping in mind I've rounded some of these in the 2 sig fig range. And I get 9.99 volts. Which again, we say we're happy because we know this is a 10 volt potential across here. These add to 10 to 2 significant figures. So I hope this video helped demonstrate how to use these concepts. Again, big ticket things. You have to realize how to simplify the circuit down. So parallel combination, add the capacitances together, you get 8. Redraw the picture. Always redraw the picture, leaving everything the same other than the change that you make. I strongly recommend you bring the color codes over too. I think the color codes really help demonstrate the potential differences in the circuit. 3 in series, you find the equivalent capacitance, the reciprocal way. Move over to here. single capacitor. Once you get it down to a single capacitor, you're basically just using definition of capacitance right here. C equals Q over V. You apply it here. And then again, the trick is knowing when you go back to the left what kind of transfers over. This charge is the charge on all three of these. Q1, Q1, and Q345 are all 14.1 microcoulombs in this problem. Then knowing how to calculate the voltages, which is just using definition of capacitance over and over and over. Then moving those voltages over to here to calculate these charges. So, hope this video demonstrates how to do these concepts. Have a great day.